Now I will talk a little bit of equivalent rectangular bandwidth (ERB), and is defined as the bandwidth of a rectangular filter shown here on this figure with same output power as auditory filter. This is a broad. This is a ERB here. Yeah, and drawing was a little bit sloppy. Here is better on the sense of hearing. This area of ERB here, ERB is the frequency broad bandwidth. This regular is have an area the same almost as the auditory filter, original filter. Okay, and it can be it's depend of the frequencies. This ERB, there's a term here is called 24.7 times somewhat another term depending on frequencies. 24.7 times 4.3 times f plus 1, and f is in kilohertz. Here mathematical, this delta f, this broad bandwidth here, times a Vmax. Vmax is a maximum here. This area is the same as the integral from 0 to infinity of the auditory filter output here. Okay. There are also some barks. It's a little bit complicated. It's the number of auditory filters. I get it here. The barks are the number of the critical bands which will cover the whole frequency range. So there should be 24. I don't know why, but this is the number of critical bands showing covering the whole frequency range. Okay. Yeah. I will not go too much in it. There's a bark. The bark is a green one, and the blue one is a ERB, and the 1/3 octave is this line here. Dependence of auditory filters, level dependence. It shows up when the levels are small. Is masker level is parameter. Yeah, the masker level is a parameter. If then at medium levels, as you see here, filters are roughly symmetric on linear frequency scales. Linear here, but at high frequencies levels, high levels, then they are more asymmetric. 90 dBs here, asymmetric, 20 dBs here, symmetric. Okay. Yeah. So then we have also normal versus impaired hearing. Could be a little bit interesting for me. Impaired broader auditory filters and the reduced frequency selectivity because of broader auditory filters, and also difficulties to segregate sounds. That means difficulties in speech, in sound, in noise. Okay, yeah. And another thing, there's some concept called signal to masker ratio, and if the best SMR filter is when you have a not noise situation, noise, and then a gap, and the SMR filter is inside here. Then the noise is using noise minimizes all frequencies listening effects. I don't know too much about it, but it should be better. Okay. Yeah. Um, so, but I will end with some very essential results. Results from masking experiments. Auditory filters excitation patterns. They are and masking results from masking experiments. Auditory filters and excitation patterns are related. How to explain this? We have, for instance, we have a sound on 1 kilohertz. It will activate many auditory filters. So the sound comes to a basilar membrane, it will activate many auditory filters. So excitation patterns is a total excitation. Yeah. So if you have 1 kilohertz sound, you have some auditory filters with center frequencies less than 500 hertz, 750 hertz, 1000 hertz, and so on. You can see here they have a line here at 1 kilohertz. Then we have this point C here is in the excitation pattern is here at 1 kilohertz. It's up here, and you can see the line. It intersects with the red line here in the point A, but the center frequency of the red line is 500 hertz, so it's on the excitation pattern is here, and then also the line intersects with the green line at center frequency 750 hertz. We are at B, so 750 hertz filter center frequency 750 hertz. We are here, and so on. And the other one here, as I talked before. And then if you have some, can we say, 1250 hertz center frequency, it's a green one. It's intersected here at D, so we go to 125 or 1300 or what it is center frequency. We are at D, and then the blue one with center frequency at 1750 hertz or something. It is intersected here in over here, so we go to the right here. So this is an excitation pattern. At low, you can say excitation patterns, the total excitation at lower levels, filters are symmetric on a linear scale, but the excitation patterns is asymmetric. So, and changes with increasing level. You have an auditory filter at, for instance, 1 kilohertz. This is one is a input of one tone swept in frequency, but it's becomes some frequencies, and the output of is at one tone along the membrane, the basilar membrane. So auditory filters, for to make it simple, is you can say it belongs to one point at the along the basilar membrane, but many different frequencies. So we have auditory filters here. So it's you more the more increasing level, so it's asymmetric, getting asymmetric, broadening on the low frequency side. Excitation patterns, it is you have one tone, but its output is along the whole basilar membrane. So and it shows up because of this figure we showed here. When the frequencies are getting higher, the auditory filters are broadening, and you get this asymmetric excitation patterns. Excitation patterns broaden on the high frequency side. here. And that's what I want to talk about now. Thank you.